Welcome back to Differential Calculus. In this video, we want to talk a little bit more about local mins and maxes. So I'm kind of assuming you've already seen them. You have some idea of what's going on if I say critical point, things like that. But now we're going to get a little deeper into it. So let me remind you about how we check for local mins and maxes. Remember that you can only have a local min or max for a function at a critical point. That's a point where the derivative is 0 or undefined. And then once you know that you have a critical point, you still have to check and see what kind of critical point it is. Is it a min or a max or neither? And the first derivative test is one way of doing that. And basically what it looks at is the function being increasing or decreasing before or after the critical point. So in this first part here, what we have, let's say this is our critical point p. Left of the critical point, that's x less than p, the function is decreasing. And then right of the critical point, for x greater than p, the function is increasing. So it switches from decreasing to increasing, and that makes a local min. And in the second part, we have increasing for x less than p. So increasing to the left of p, decreasing to the right of p, and that gives you a local max. That does not depend on the function being differentiable at p, right? We only talk about x less than p and greater than p, but not at p itself. So the first derivative test is great. We kind of love it, but it's not perfect. So let's talk about some pros and cons. One thing the first derivative test is really good for is that it always works. There's always something to be said for a test that always works, right? You can always, if you want to, use the first derivative test, and it will tell you what is going on at the critical point. Pretty nice. It's pretty nice. It also has the feature that you only have to take one derivative. So you don't need to take 2 or 3 or anything more than that. You just need the first derivative test, and you can do this. Unfortunately, the first derivative test has a couple of drawbacks. One, it's kind of a lot of work. You have to make this table and figure out the derivative at all these different points just to find out about one value. So it's a lot of work sometimes, you know, especially in certain situations. And the worst thing about it is that it does not, absolutely does not extend well to higher dimensions. So it works fine for functions in one variable because you can only come into p from one side or the other, from the left and the right. But if you have a multivariable function, which you might if you take, say, multivariable calculus, then you might have some sort of surface or something like this where I have like a dome shape, and I'd still want to find a maximum, but I can come in from all sorts of directions, right? I can come in like that, or I can come in like that, or I can come in like that, or like that. And you don't want to have to test all the infinitely many directions you could come in. So first derivative test isn't that good. Well, it's not very good at all, really, in several variables, in multivariable calculus. So fine. What else could we do? I'm not saying the first derivative test is bad. I love the first derivative test, but it's nice to have other options. So the other way we can think about it is if we're looking for a max or min of a function, instead of looking at increasing and decreasing, we can look at concavity. So let me remind you how concavity works. If you have, well, it's related to the second derivative. If you have f prime of x greater than 0 near x equals p, what does that look like? Remember, that's concave up. Remember, second derivative positive means concave up. So if this is my point P and it's concave up near there, it looks like a smile, right? Yes. And conversely, or maybe not conversely, but the opposite of that is if the second derivative is negative near x equals P, then f is concave down. Which means something like this. So maybe here's my point P, and the function is concave down there. Okay, concave down looks like a frown. Okay, so this, you can probably see there's a max and a min on this picture, right? This gives us a test for maxes and mins that depends on the second derivative. So we call this, somewhat fittingly, the second derivative test. It has a little bit stricter requirements than the first derivative test. So for the second derivative test, you need the function to have a second derivative at the critical point. Okay, so you only do this at a critical point. Just like before with the first derivative test, you have to check you have a critical point first. Once you have that point, then you check what kind of point it is using this test. Okay, so we need a continuous second derivative, And then, well, if the second derivative is positive at the critical point, then f has a local what? So see if you can fill in these two blanks. Second derivative positive means a local, go ahead and pause, I'll let you think. Okay, so this is a little bit counterintuitive. If the second derivative is positive, the function is concave up. That makes a local minimum. Right? The picture would look like this. Here's p, concave up, local minimum. Okay, so we already know the derivative is 0 there because p is the critical point. We just need to know, is it a max or min? And now if the second derivative is negative, then that's going to be the opposite. That's going to be a local max, because now at this point where the function is flat, it's also concave down. Okay, and it turns out since the second derivative is continuous, being the second derivative positive at p implies the second derivative is positive nearby p as well, because, well, that's how continuous functions work. If it's positive at some point, then it's positive nearby. Okay, so great. This is a fabulous test. It does have some stricter requirements, so it has some cons and some pros, just like the first derivative test. Let's look at the cons first. Well, the biggest con is it doesn't always work. For example, if you have a critical point where the derivative doesn't exist, then the second derivative certainly doesn't exist either, so you can't use this. Okay, it's not as general as the first derivative test. Another big con is that it requires you to take second derivatives. So sometimes you have a messy function, and then the first derivative is pretty messy, and then taking the second derivative is even worse. So you're like, oh, this looks horrible. Why would I ever do this instead of the first derivative test? Well, it has a lot of nice features too. Oops, I didn't mean to write first. Just cons. I said first. So what are some pros? This extends really well to higher dimensions. So it's good to know it now so that when you see it in multivariable calculus, it makes a lot of sense. And if you have, especially if you have somewhat simple functions, it's easier to use. So if you can manage to easily take a second derivative, like if you have a polynomial or something, second derivative test is often easier because all you have to do is plug in that single point to the second derivative instead of evaluating on the left and the right and drawing a number line and all that first derivative test stuff. Okay, so a lot of times second derivative test saves you work. But in any case, you can always choose to use the first derivative test. Second derivative test is just a nice option sometimes. So let's go ahead and try it. Say we have a polynomial x to the fifth minus 5x plus 3, and we want to find all the critical points, or find all the local extrema. Extrema means max or min. So we want to find them, and for each one, is it a max or min? That's what the classify means. Okay, so find the critical points, well, or find the extrema. Where are they? What are the x values? And then classify it. Is each point a max or a min? Okay, so let's get right down to it. We're going to need the derivative, right? So we know the power rule. This is pretty easy. Good thing we learned all our differentiation formulas. We wouldn't want to use the limit definition on this, right? Okay, so there's the first derivative. And since we're going to use the second derivative test, let's just go ahead and take the second derivative now. That's going to be 20x cubed. Notice that that wasn't very much work, right? For lots of functions, second derivative is not too bad. Okay, so what do we need to do? First, we need to find the critical points. You always have to find critical points first. And those happen where f prime, the first derivative, is 0 or undefined. Since it's a polynomial, it's defined everywhere, we just need to set derivative equal to 0. So we'd figure out 5x to the fourth minus 5 equals 0. Divide everything by 5, so x to the fourth minus 1 equals 0. And we can factor that into x squared minus 1, x squared plus 1. That's our old friend a minus b times a plus b equals a squared minus b squared, with a equals x squared and b equals 1. Okay, so that equals 0. This term, x squared plus 1, is never 0, right? You're taking x squared, which is greater than or equal to 0, and then you're adding to it. So that's never going to give us a 0. On the left, we have x squared minus 1. Well, that factors into x minus 1, x plus 1. And then we still have the x squared plus 1 there. So the only ways we're going to get 0 from this function is if x minus 1 is 0 or x plus 1 is 0. That tells me x equals 1 or x equals negative 1. So we could use the first derivative test here. We could make a number line and check some points in between -1 and 1 and outside of them and all that. Or we could use the second derivative test. F double prime of -1 is negative. I don't even care that it's -20. All I care is that it's a negative number. So I'm just plugging -1 into that x, and F double prime of 1 is positive. See how easy that was? Very, very easy. That's the benefit of the second derivative test. Very, very easy. Okay, so x equals -1. We have a negative second derivative, so the function is concave down, which means f has a local max. And then at x equals +1, at x equals +1, and then at x equals +1, well, now the function is concave up and flat because the first derivative is 0. So we have a critical point where the function is concave up. F has a local min. We know those are the only places because Fermat's theorem tells us since we only have derivative 0 at those 2 points, those are the only places we could have a local max or min, and the second derivative test classifies them for us. Okay, so the second derivative test is not perfect, unfortunately. It doesn't always work. So let me show you a couple cases of that. Let's look at these two functions. One of them is x cubed, the other is x to the 4th. So what happens if I look at g of x? Let's take the first derivative, g prime of x, 3x squared, very good, and g prime of x, g double prime of x would be 6x. Okay, so the only critical point is that x equals 0. If I draw the graph, notice that g prime is always positive because it's something squared times 3. So the graph actually looks like this. It flattens out and then it keeps going up. Okay? If I try to do the second derivative test, then I would do g double prime at the critical point, so g double prime of 0. That's also 0. So the trouble here is that this is an inflection point for the function, and it's a critical point, but the second derivative is 0 means the second derivative test is entirely unuseful. We call it inconclusive. Okay, so you could still use the first derivative test, right? You can see that it's increasing on the left over here, and the function is increasing on the right over here, so it doesn't switch from increasing to decreasing or vice versa. It's not a max or min. But the second derivative test won't tell you that. The second derivative test just tells you nothing. Okay, but that's not the only time the second derivative test can tell you nothing. So what if we look at f is x to the 4th? So f prime of x would be 4x cubed. If we set that equal to 0, that means, again, x equals 0. So do you think this is an inflection point? Do you think that, what's going on here? So now the second derivative would be 12x squared. That equals 0. Don't set that equal to 0. So if we do f double prime at the critical point, we get 0 again, just like in the first case, right? But this is not an inflection point. So now f double prime being 0 is still inconclusive. This function actually looks like this. It looks like a very flattened out parabola, x to the 4th. This is a local minimum. The second derivative test just didn't figure that out. Okay, so if the second derivative equals 0 at the critical point, you just get no information. Could be a max, could be a min, could be nothing. You just have to do more work, which usually means first derivative test. Right? The first derivative test would work here, because if you put negative numbers into x cubed, you get negative, so the function is decreasing over here. And then if you put positive numbers into x cubed, you get positive derivative, so the function is increasing. The first derivative test works fine. It's just the second derivative test inconclusive. Okay? So we will do a lot of practice with this in class, and then we will use it to great advantage when we optimize things, and I will see you then.